Welcome to Calculus BC. In today's episode, we're going to be discussing Chapter 8.3, which is Exponential Growth Revisited. And we're going to start off with our quintessential differential equation for exponential growth, and it looks like this. And usually we're going to know how to set this up because if we ever have to integrate something like this and find out what the actual equation was, the word problem that's going to signal us that this is going to be the case is going to be some phraseology that follows the following kind of thing, where we have population growing proportional to the number of whatever present. And so hopefully that phraseology kind of makes sense, because the larger a population is, the faster it's going to be inclined to grow, right? If we had 2 bunnies versus 64 bunnies, where we're going to be able to grow bunnies even faster with 64 rather than just 2. So the population does in fact grow proportional in size to however many things were present at the time. And so we often refer to this K, we call it a constant of proportionality. Proportionality. All right, so that's going to be, this type of phrase is going to be what signals you to do this. Now, what exactly does this integrate into? Well, we've seen this model before in Calculus AB, and in a couple lessons ago, there was one that did kind of model this. It was like some Christmas tree or something like that. But let's go and integrate this thing as a general function to find out exactly what he's going to become. So I'm going to go and separate the terms like I always do. I'm going to have 1 over y dy equals k dt. So I just separated the terms from one side to the next. I'm going to integrate both sides. And what that gets me is, it gets me the natural log of the absolute value of y equaling kt plus c. And so now in order to get the y by itself, I'm going to go ahead and change forms back to exponential forms. So the absolute value of y is going to be equal to e to the kt plus c. And we saw this happen in the Christmas tree problem and in the last couple episodes, where we have 2 exponents being added together. So I'm going to reverse engineer that idea and say that e to the kt times e to the c will be equal to the absolute value of y. This guy will turn into c, right, because e raised to a constant is in fact a constant. Now, sometimes people tend to use different letters for this. I tend to use c the whole time. It's just kind of a different style. And now I've got the absolute value of y equaling c, and we know that that would be plus or minus c, but everything gets resolved out as long as we keep c the constant that it's supposed to be. Now at this point, this should look pretty familiar. This is our classic, from Integrated 3, our exponential growth formula. Some of you may have learned it in a different way. Some of you may have learned it as PERT formula. In other words, like A equals PE to the RT. Hopefully you can see the corresponding pieces and how they associate with each other. Some of you may have learned Y equals Y naught E to the KT. It's all the same things. Hopefully you guys can make the associative pieces. They're all kind of the same, but this formula is extrapolated by use of integration and differential equations. So we will use this formula in a couple of examples. I'll be right back with them, and then we will get started. I'll see you in a bit. All right, so in this example, we're going to be talking about a cell of bacterium E. coli, which divides into 2 cells every 20 minutes, one placed in a nutrient culture. We're going to let y of t equal the number of cells that are present t minutes after a single cell is placed in the culture, and we're going to assume that the growth of the bacteria is approximated by an exponential growth model. So what we're going to do is we're going to find an initial value problem whose solution is y of t. So the initial value problem is pretty straightforward. It's just going to be dy over dt equals ky, with y of 0 equaling 1. So how do I know y of 0 is equal to 1? Well, they talked about a single cell being placed inside the culture, so I have to assume that time equals 0. That's when that single cell happens. And so there's my initial value problem. Now it says find a formula for y of t. So that's actually been a pretty extensive kind of thing here. So what I'm going to do is I'm going to integrate this thing, and I know he becomes y equals ce to the kt. Well, what do I know about this? If I know that this is ultimately what this guy's going to integrate into, well, I know that when time equals 0, I have 1 culture, so that allows me to solve for c pretty quickly. So I can say then that 1 is equal to ce to the k times 0, and anything to the 0 is going to be 1, so I know that 1 is equal to c. So my formula is going to be y equals 1e to the kt power. So that is going to be my formula to find out how much bacteria is going to be there at any given time. Part C is asking me about how many cells are present after 2 hours. In order for me to figure this out, I'm going to want to solve for K in this problem here to find out what the rate of growth actually is. So how do I do that? What I'm going to do is I'm going to set the 2 cells equal to a single cell, because the problem told me that the E. coli doubles every 20 minutes. So I'm going to say 2 equals 1e to the kt. And I'm going to go and proceed forward like an integrate 3 problem and solve for k. So there's no way that 2 and e are going to have the same base. So I'm going to go ahead and natural log both sides. So I end up with the natural log of 2 equaling k times, in this case, t is actually going to be 20 and not t, because I know it takes 20 minutes for this to happen. And I'm going to get k equal to ln of 2 over 20. And I'm going to go and leave this here as my rate of growth here. I don't want to end up with a rounding error at the end, so I'll go and just leave them there. At the end of the day, I'm going to put all this stuff into a calculator anyway. And so what this is this is y equals 1e to the kt, where k is actually a known value now. So I can go ahead and figure that part out. So in order to find out how many cells are present after 2 hours, I got to make sure that I'm very clear. My time interval is actually in minutes, so I'm not going to plug in 2 for t. I'm going to plug in e to the k times 120 minutes. And so 120 is going to multiply by this thing, and I'm going to raise e to it. At the end of the day, after all that's calculated, I'm going to have 64 bacteria present after 2 hours. So that should take care of part C. Part D is asking how long does it take for the number of cells to reach 1 million. So how long does it take? Means we're going to solve for time. So I'm going to say, well, 1 million is equal to e to the kt. Again, k is equal to this ln of 2 over 20. So I'm just leaving it as k just to make things simpler for me. I'm going to ln both sides. I've got ln of a million. 2, 3, 1, 2, 3, yep, like that, equals kt. And now I'll go and divide by k. Again, k is this number right here. So keep that in mind here. So what I've got is the calculation of all of this. And when I calculate all that, I end up with 150.41 hours. In order for the number of cells to reach 1 million. So hopefully this E. coli problem makes sense. I'll be back in a few seconds with the next example. In this next problem here, we're talking about polonium-210, which is a radioactive element with a half-life of 140 days. Assume that 10 milligrams of the element are placed in a lead container and that y of t is the number of milligrams present t days later. So it does say find an initial value problem whose solution is y of t. Again, we're just going to kind of go back to what we know. dy over dt equals ky. And we know that in this case, we know that y of 0 is equal to 10, right? That's the initial value. We're placing 10 milligrams into the container. We've got to find a formula for y of t. So how do I do that? Well, I know this guy integrates, again, into ce to the kt. In order to find out what c is, I'm going to go and place 10 as y. ce to the k times 0, that's going to go away, so c equals 10. So I know that y equals 10e to the kt. Now this is actually a half-life problem, so I can probably solve for k right away, especially because part C is asking me to find out how many milligrams are present after 10 weeks. I should probably find out that value of k. Well, if my initial value is 10, hopefully it makes sense that 5 will be present after 140 days. So I will go ahead and solve. I'll get 1/2 equals e to the 140k, ln both sides. So I've got the natural log of 1/2 equals 140k. Divide the whole thing by 140, so my k value is equal to ln of 1/2 over 140. And just like the E. coli problem, I'm probably just going to keep that as k, just knowing that when I plug this into the calculator, that's going to be what fills in the role of k. So my formula really is 10e to the kt, but now again, k is this known value. So now it's asking me how many milligrams will be present after 10 weeks. There they go again with this unit conversion stuff. T is measured in days. And so after 10 weeks, this is really 70 days, right? So I know that T is going to equal 70 in this problem here. So how many milligrams will be present? I'm going to say Y is equal to, looks like 10e to the K times 70. And after those calculations are done, that's going to end up being approximately 7 milligrams present. And yes, I did do that one in a calculator, and I rounded. Okay, so now they're asking us, how long will it take for 70% of the original sample to decay? Well, remember, we started off with 10. So if 10 is how much I started off with, and 70% is gone, that means that 30% is remaining, which means only 3 will remain. And so now I'm going to go ahead and divide by 10. And I'm going to get 0.3 is equal to e to the kt. Again, k is a known value, right? So I'm going to do the natural log on either side. And I get the natural log of 0.3 equals kt. So if I divide by k, I'm going to get t equals, and if I divide all that stuff out in a calculator, I get approximately 240.8 days. And that should take care of exponential growth. Again, this should be largely a review, so hopefully it made enough sense, at least for you guys to get your bearings back on exponential growth. That will wrap it up for this episode. In the next one, we will cover something a little more realistic than exponential growth, but we'll save that for the next one. As always, please leave comments or questions in the comments area. I will see you all in the next episode.